Hello, everybody. Welcome to our final episode of this MathWorks mini-series for this particular season. We're going to go ahead and get started in just a couple of minutes, but we're going to wait for some folks to join us. And welcome to the other folks that have just joined us. We're going to go ahead and get started in just a couple of minutes. If you've got any questions about this topic or anything related to MathWorks or RoboNation, feel free to plop those in the chat, and we will answer those at different times throughout our webinar. But thank you again for joining us. And again, we'll get started in just a couple of minutes. Thank you, everybody, for joining us. We're going to go ahead and get started in just 1 or 2 minutes while we wait for some more folks to join us today. We're excited to be kicking off our final episode of our MathWorks mini-series that we've had early this year, and we're excited to dig into the subject. But while we wait for some folks to join us, feel free to put any questions in the chat, and we will get through those throughout this session today. Thank you. All right, well, I'm going to go ahead and kick off today's webinar. My name is Alicia Gavin, and I am the Director of Communications and Marketing here at RoboNation. RoboNation is a nonprofit organization that focuses on robotics education, trying to bring hands-on experiences to students from the K-12 space all the way up to university and postgraduate programs. So we've got robotics programs underwater, on top of the water, in the air, on the ground. We've got a little bit of everything here at RoboNation. But we believe that we are a robotics community, and that takes a lot of different folks to make that possible. It's an ecosystem. So not just for you students, but we've also got educators, mentors, advisors, judges, and folks from industry, as well as a lot of our industry partners that serve as sponsors here at RoboNation. So we're excited to be welcoming one of those very sponsors tonight. We've got Abhishek Shankar from MathWorks, who's going to be joining us this evening for our last episode of early this year's MathWorks mini-series to talk about determining direction of arrival of an acoustic beacon. So estimating the direction of arrival is a common problem in surface and underwater competitions. In this webinar, we'll be using a towed passive sonar array to detect and estimate the direction of arrival of an acoustic beacon. So I know that I could keep going on about RoboNation and all the fun stuff we do, but why you're here is for Abhishek and all the fun stuff he's going to talk about. So I will go over and pass it to him.
Thank you, Alicia. Let me quickly share my screen. All right. Again, thank you, Alicia, for that introduction. Hello, everyone. I'm Abhishek Shankar. I'm here to talk today about estimating direction of arrival of an acoustic beacon. Uh, a lot of you might be participating in robotics competitions, especially with RoboNation. So if you're in RoboSub or RoboBoat or even RobotX, one of the tasks that you might have faced before is to locate a random finger that's located somewhere under the water. In this webinar, I'm going to be talking about how we can simulate an acoustic underwater beacon. So that involves modeling a beacon underwater and also calculating the transmission paths because when you have a beacon underwater and then it's emitting sound, it's going to be reflecting off of the walls of the pool, of the floor, and also all the other objects that you might have, like buoys and gates, etc. So there's going to be a lot of interference and signals bouncing off of each other. So I'll talk about how we can calculate these paths. And then I'm also going to talk about how we can simulate a passive towed array to record the received signals. Um, a passive array of hydrophones is often used in a lot of marine applications. You might have used one yourself. It may not be a linear array like you can see in this image here. It could be, in any configurations. And I'll also talk about how you can choose the right configuration for your application because there's different ways that you can model your hydrophones, and every configuration has its own strengths. And based on your application, you might go with one or the other, but I'll show you how we can do that with some of the apps in MATLAB. All right. The last one we're going to do is of course the main part, which is using the direction of arrival algorithms to estimate the direction of the beacon. MATLAB has a bunch of algorithms inbuilt that you can use to get the direction of arrival. Again, all of these are available with you with the free MathWorks license as part of our sponsorship to RoboNation. So if you're competing in any of the competition, you can request free software for MATLAB, Simulink, and 100+ toolboxes that you can use. And yeah, enough of slides. I'm going to switch to MATLAB. Let me quickly switch to MATLAB. Yeah. And I'm going to be opening up. Sorry, not one. I think you just saw the results of what I was going to show you. But yeah, this is what we're going to be working with today. This is already a built-in example with the MathWorks. I can share the link to you in a bit. So if you just search for locating an acoustic beacon on Google, this will probably be one of the top results that you'll find. So I'm going to walk you through the example. So it's got a lot of different things going on here. The first, like I said, we're going to be simulating both the beacon and the passive array. So that means the waveform from the beacon, how the beacon propagates through the water body, and also how the passive array is going to receive all these signals. And then we'll plot the received signal. And then finally, we'll go to estimating the direction of arrival. To set the scene a little bit, we are taking a simplistic pool surface. As you can see, there are no other obstacles. It's just a beacon located 1 meter above the bed or the floor of the pool. And then we have a boat that is towing a passive array. So if you're in a RoboSub competition, you might already be underwater with your own hydrophone. But if you have a boat, it's typical to have like an arm or an extension that goes underwater with the hydrophones placed on those extensions. And here we have set the pool to be about 200 meters deep. It's a pretty deep pool. Obviously, for competition purposes, you can set it up because it's not going to be as deep, but we wanted to show you how we can simulate it in an extreme deep environment. And the beacon here is going to be modeled such that it's going to emit an acoustic, uh, it's going to transmit an acoustic beacon uh, at 37.5 kilohertz, and it's going to do a 10 millisecond pulse every second. And then it's also going to be modeled as an isotropic projector. So what an isotropic projector means is that it's going to have the signal strength same in all direction. So if you have a beacon, it's going to be propagating in all directions. So imagine a sphere around the beacon, and there's going to be, the signal is going to be same in all directions. So this is pretty common, but you can also have different kinds of projectors. So you can have something that is like in a cone shape. So you basically cut off the projections in other direction except a small angle that is also used to have like a very specific beacon sent in a particular direction. And there's also the isotropic one, which is more common, which has the beacon the signal is going to be transmitted in all direction with equal strength. And the towed array that's going to be attached to the boat is a uniform linear array. So as you can see, all the five hydrophones are in a straight line, so along the y-axis. So it's a linear array of hydrophones, but there are different configurations that you can use to set that. I'll come to that in just a bit, but first let us go ahead and define some of the properties of our beacon and passive array. The first one is the propagation speed. I'm going to be setting it to 1520. This is in meter per seconds. This is the propagation speed of sound underwater. It's close to 1500 meter per second. Again, it depends a lot on where, if it's ocean water, if it has a lot of salt content, or if it's just pool water. So the things affected, the composition of your water affects it, but it's generally close to around 1500 meter per second. And we're going to set the channel depth to 200 meters because we are assuming the pool is 200 meters deep. And the operating frequency is set to 37.5 kilohertz, as I had mentioned before. Right. And the first one that we're going to do is specify all the paths that the beacon can take. So I'm going to be using the ISO speed underwater paths from the phased array toolbox. Um, Actually, before I go into what this does, let me quickly show you what the phased array toolbox does. I think it might be relevant to a lot of you. Just Google phased array. So this is one of the toolbox that is included in your free license. What you could do is you can design phased array systems. You could do direction of arrival estimation, which is what we're going to do. You can also design waveforms and synthesize signals. And you could do radar and sonar and all this cool stuff with this toolbox. So it's really useful when you're working with like phased array sensors like hydrophones, radar, sonar, ultrasonic, and all this different systems. And if you've never used this before, I'd highly encourage you to go check it out. Again, it's included in the license that you have along with RoboNation. So you should have all the functionalities and all the apps that come along with it. Right. Let me get back to MATLAB. So from the phase array toolbox that I just showed you, we're going to use the ISO speed underwater paths function, which will define all the paths. And you can set the number of paths that you want to simulate as a property, and then the value to whatever value that you want to set. I'm going to be setting it to 10. So we're going to assume there's going to be 10 different paths that the waveform is going to take from the beacon to the passive array. But again, you can increase it, decrease it based on the complexity of your environment. And then we will use the multi-part channel and set the operating frequency to know that the signal is going to be propagating through this channel at this particular frequency. Let me quickly run this section. So I'm going to be running the section along as I talk about it, so that all these parameters are defined, and so it's easy to move along. So once we have that defined, the next step is to define the acoustic beacon and the passive array. The acoustic beacon, before we go to the beacon, let's do the waveform first. It's going to be a rectangular waveform with a 1 second repetition interval. So we're going to set the PRF to 1, and PRF is the pulse repetition frequency. And then the pulse width, or the width of the rectangular pulse, is going to be 10 milliseconds. So it's 10 raised to the power minus 3. And the bandwidth is just 1 by the 1 divided by the width. And the frequency, or the sampling frequency, is going to be twice the pulse bandwidth. And you can then use the rectangular waveform from the phase array toolbox and pass in all these properties that we just defined to create your waveform, and then set the sample rate to what we had just defined. So far it's pretty simple. We are defining the paths that the beacon is going to move in, and then also the waveform that's going to move in those paths. And now we'll come to the acoustic beacon, which is this black dot over here that you see. So in RoboNation competitions, you'll have a beacon randomly located in your pool. Here, obviously, since I'm simulating it, we know beforehand where it is located. But when we go to the direction of arrival estimation, we are not going to know where it was located, and we'll just look at the received signals to estimate the direction. But for the modeling purpose, we're going to model it as an isotropic projector. Again, that means it's going to have the same signal strength in all directions. And then it's going to radiate along along with the propagation speed set here and the operating frequency that we had defined here. That's, I think, 37.5 kilohertz. And of course, the beacon platform is located 5,000 meters in the X direction, 2,000 meters in the Y direction, and then negative 199 meters in the Z direction. So it is 1 meter above the floor of your pool bed or seabed. I think seabed is more appropriate because our distance is in like kilometers. But essentially, this is a huge location that you're looking at, and the beacon is set like 5 kilometers away, and it's emitting the pulse, emitting a rectangular pulse, and we're gonna try to figure out where it's coming from. Once we have this, we'll go into the passive towed array. Again, the towed array here is a linear towed array, but I'm going to show you ways on how we can, choose the configuration for your hydrophones. The linear is probably the most simple one, but let me quickly go to MATLAB, go to apps, and then if you scroll down to signal processing and communication, there should be an app called Sensor Array Analyzer. So I'm going to click on that. And what this app essentially lets you do is model your sensor system. So if you have, let's say, five sensors, 5 hydrophones, you can do it as a ULA, which is uniform linear array, or you can also do it as a uniform rectangular array, uniform circular array, hexagonal circle, like planar circular, and also concentric. So it gives you multiple ways to arrange your sensors. And you could also do, so this is all in 2D, right? It's going to be how you place your sensors in 2D. But if you want to have a 3D arrangement of your sensors, so if you have a really complex hydrophone system that has like, 100 hydrophones more located like a sphere, you can use these, but you can also do arbitrary, which is, you can define where each of them are located. So you can see the element position given here. So you can set all of them and then get your sensors in any arbitrary configuration that you want. So I'm going to switch back to linear array right now. But these are different ways that you can set your hydrophones. But next, I'll show you how we can check if that would be a good configuration for your system. So once you've chosen the configuration, let's say it's linear, and I'm gonna have like five elements in this, and the spacing is gonna be 0.5 meter. I can change it to 0.1 meters. But you also have an option to set your spacing as a function of your wavelength. So again, these are two commonly used metrics when it comes to designing sensor arrays in the signal processing field. So depending on what you want to model it as, you can choose meters or wavelengths. And then your array axis is the axis along which your sensor is going to be arranged in. So here I've chosen along y-axis. I can change it to x-axis, for example, and then you can set like the frequencies and the propagation speed, and then hit apply. And what you can do after this is you can look at the 3D pattern. Oh, actually, before I talk about 3D pattern, I forgot to set one important thing, which is that it has a hydrophone. For our example, we're going to be obviously modeling in a hydrophone, but with this tool, with this app, you could do microphones, antennas, polarized antennas. So any different application you want, you'll have something that you can choose for your application. And for us, it's going to be a hydrophone. So let me select a hydrophone. And then again, the 3D pattern visualizes the what kind of signals that it can receive. So if you look at this, you can see that since the array is is arranged along the x-axis, you're gonna find all the signals coming from around the x-axis. So if this is your sensor array, you're gonna get signals from all the other directions, but not directly in front of the x-axis, because if you think about it, if you look through the x-axis, you're gonna only hit one or two sensors, right? So it's not gonna give you as much coverage as along the like a circle along the x-axis. So this is something that you can use to determine if this configuration would work for you. Again, you can play around with different configurations and see how the pattern would be. And you know, there's like a lot of experimenting going on in these kind of situations, because a lot of times you don't know where the beacon is, or what situation you'll be in. So you'll have to play along with the parameters and then figure out what configuration works for you. That's actually one of the advantages of simulation, because you can simulate different kinds of sensor arrays and see how it would receive the pinger signal and then use that as a starting point for your hardware design. Obviously, there's going to be differences in simulation and hardware, but you could ideally reduce the time taken to come up with your final design if you use some sort of simulation in your design process. And I'm sure most of you are aware of this, because I've seen like a lot of reports where you guys do a lot of simulation stuff, fluid analysis, dynamics, and all these things. So you are pretty familiar with the importance of simulating things before, going ahead and building it in hardware. I am gonna close this one. Um, But that's what you can use to simulate your sensor, and you can also export it to your workspace. Now let me quickly go back to the live script. Uh, excuse me. So the toad array in this system is going to be a linear system, so it's going to be arranged in a straight line. And we're going to set the hydrophone voltage sensitivity to a negative 150. And the phase array is the ULA from the phase array toolbox, which is the uniform linear array, is going to have all these parameters. You basically said that it's an element. There are five. The element is an hydrophone. There are five hydrophones, and the speed and the spacing is the propagation speed divided by 2 times the operating frequency. Excuse me. This is a pretty common formula used in signal processing. But again, you can also play with the element spacing because depending on your spacing, it can really play a big part in how your received signal comes out to be. And then again, you defining the collector, which is going to be a sensor array with these propagation speed and your operating frequency. And the array platform is going to be initially located at a negative 10. So it's going to be at the origin in X and Y, and then a negative 10 from the surface of the water. So it's 10 meters below the surface of the water. And it's going to be moving at a velocity of 1 meter per second in the y-axis. So this is velocity in the X, Y, and Z. And we're going to be moving the boat 1 meter per second in the y-axis. So this is our simulated passive towed array. Um, Let me run these parts real quick. And finally, each of these hydrophones usually have a gain with them. So any signal that comes in, it's amplified. We're going to set the gain to 20 and the noise figure to 10. And then we set the sampling rate, and we're going to set a constant seed so it is reproducible. So I'm going to run that as well. Now that we have the acoustic beacon, the acoustic waveform, and the passive array simulated, we can go ahead and simulate the whole system. So what we're going to do is we define the waveform, which we had already set here, a rectangular waveform. And we're going to take 10 pings from the beacon, and we're going to record the responses by the towed array. So what we do is we get the position and the velocity of the beacon and the array platform using the functions here. These we had already set right here. So these are the platforms. So you can just use that and then the pass in the repetition cycle, which is 1. And then you could do ISO paths, which is also something that we had set way at the top right here, which is all the, if you remember, it's all the paths that the waveform can take. We're going to use that and then pass in the positions of the platform, positions of the transmitter and the receiver. So the beacon and the passive towed array that we got from the previous 2 steps. And this will give you the paths that it would take to get to you. The Doppler factor, which tells you how much the frequency has shifted from the source to the end, and the absorption loss, or how much it was, how much signal loss that took place in the water, and then the receiving angle and the source angle. And we're going to use all these parameters to propagate the acoustic beacon waveform. And then we're going to use the array collector that we just defined here for our passive towed array to get all the received signal and save it in this variable rxsig. So this is basically simulating the whole system. It is transmitting the beacon, and then it's going to take the paths that we had defined previously. So it's going to take all the 10 different paths that we had defined, and then we're going to use that to determine how the received signal would look like in a passive system with 5 hydrophones located in a linear way, and then we're going to record all those responses in this variable. And let me quickly run this. And once we have that, we can now plot like one of the responses. Since this has multiple propagation paths, it's going to be a superimposition of all the paths that it took. So you're going to see some noise and some different peaks, but you can see one clear peak, which is the time at which the hydrophone system, your passive towed array, got the peak. So this is the the prelude to what we are going to do next, which is the direction of arrival estimate. And in most competitions, all of these things you don't have to do because you don't have to simulate a beacon. You don't have to simulate a towed array because in the competition you will have an actual beacon and you'll have your hydrophone. So you will already get this waveform. You will record the signal to your hydrophone, and then it'll look probably something like this. There might be more noise depending on the hardware. Mine is a simulated system, so noise is pretty low, but in an actual system, you're going to have more noise. And if you hadn't been in my previous webinar, which was about filtering these noises, you can go check it out. But I talk about how we can, filter the noise out of your sensors and then use that for further further algorithm that you're using the sensor. Um, yeah, so now that we have come to this part, is there any questions that I can answer?
Yes, we've got 4 questions.
Okay.
One of them, I think, can be answered by what you just said about checking out one of our other webinars about filtering noise. But we've also got one was how can we adapt algorithms used in towed passive sonar arrays for smaller onboard hydrophone arrays on AUVs?
So the system really doesn't change a lot. So if it's stored, the only thing that's gonna be different from a Toad and a onboard system in an AUV is that your depth is gonna change, right? Yeah, the depth change based on the speed of your AUV. So if you're going down in the z-axis, you're gonna change the speed there. So what you would do is change the speed in the array platform over here. So if it's moving in the z-axis or the depth will change, so that would also change. And also you can change the configuration because I've seen a lot of RoboSub, uh, the the hydrophones are usually modeled as like a uniform rectangular array. So you have like 4 hydrophones in 2 by 2 matrix. But depending on how you model your system, you can set it up uh, from the app that I showed before. But ideally, you should not see a lot of change between a passive and an onboard array.
Awesome. Our next question was, how does ambient noise affect accuracy in shallow water? Um,
Yeah, noise is always going to play a part in shallow water, in even in depth. Actually, there's going to be some noise. It's unfortunately not something that you can easily get rid of. You'll have to do some signal processing to get rid of the noise. One way that I would suggest is remove the beacon and then just put your hydrophone in the depth that you'll be operating in and record the signals. That would be your noise because that doesn't have any real signal. It's just all the background noise that's going on. So you can use that to kind of determine what the frequency of your noise is and where you need to use that to design your filters. Um, you could also take a beacon if you have one and then move it in different directions. If you already know the directions, then you can use that as well to determine which is actual signal and which is noise. So in an actual system, there's always going to be some bit of cleaning up that you'll have to do with signals. I'm sure you guys are aware of this. It's pretty much common in all kinds of sensors, not just hydrophones, but it's unfortunately something that we'll have to deal with. There's a lot of different things that you can do in MATLAB to filter those noises. But if you have hydrophone record readings for your AUV, you can also reach out to me. I can help you design some noise filtering algorithms and also some directional variable algorithms.
And we've also tagged in here, we'll have Abhishek's email, the MathWorks license information, and then our first two webinars from this series will be tagged in this in the chat as well. Our next question was, how sensitive is DOA estimation to sensor placement errors?
Uh, that's a good question. So sensor placement error obviously does play a part in the direction of variable estimation, but as long as the error is low, you should not see a big difference from like the direction of variable estimate and the actual direction. You can definitely um, it's hard to say how big of a factor that would play, but usually with what I have worked with, a little error because it's very hard to get the correct placement of the sensor. So there's always going to be some error in that measurement, and you can usually work around that. It's not something that is big and that you'll have to worry about a lot. It should be pretty easy to fix that. But if you have a large enough error, then I would definitely recommend making sure that you try to reduce that error as much as possible, rather than, filtering stuff from the response.
And then our last question for now, and of course, make sure you guys are putting your
Mhm.
questions into the chat. But the last question right now is, what's the purpose of using array collector after channel? Is it modeling beam forming or is it just sampling delay effects?
Ooh, that is something that I have not had a lot of experience with, but thank you for asking that question. If you can email that to me, I can get back to you. We have some experts in beamforming and the other aspects of signal processing that can probably help you with that. I can put you in touch with someone who is, expert in that field, and they'll get back to you within a day.
Yeah, and Mac, because I think you were the one that asked the question. So if you can email Abhishek, his email is in the chat, and he will be able to get you an answer for that. Thank you.
Yeah. All right. Thank you, Alicia, for reading out the questions, and thank you guys for asking these questions. Uh, so I'm going to be moving on to the next part, but if you have more questions, feel free to drop it in the chat, and then we'll address it at the end of the webinar. All right, so the next step is the fun part, which is, estimating the direction of arrival. So if you're in the competition, this is where you probably start. So you won't have to do all this step that I just did, because you know, you are more fortunate than me. You have a hydrophone and you have a beacon and you can get all the responses and you don't have to do the simulation stuff. Um, but for this webinar, we're going to try to estimate the direction of arrival of the simulated beacon. And what we're going to do is use the music algorithm that is inbuilt in MATLAB. So I'm going to quickly switch and then show you some of the stuff that we have inbuilt that you can use. Um, Right. So in the phase study toolbox, there are a bunch of different algorithms that we have for direction of arrival estimation. So for a specific array geometry, like the linear array or circular array or rectangular array, we have few different algorithms that you can look into. You have the music estimator, which is what we'll be using for this webinar, but you also have the beam scan estimator. You have the MVDRE estimator. And then you also have the sum difference monopulse tracker. And if you're using an arbitrary geometry, then you also have all these different algorithms that you can use. So I would play around with a bunch of them. If you're pretty good at signal processing, you should have no issues just setting all these parameters, but we also have great documentations. If you're not really familiar with how to work with these algorithms, you can just look at our documentation. It's pretty detailed, and of course you can reach out to me either through email or through Discord. I'm in the RoboNation community, so feel free to reach out and I can help you out with how to use these algorithms to determine the direction of travel. Right. Going back to the music algorithm, we're going to be initializing the system object with the sensor array that we have and the propagation speed, the angles that we got. So it's going to be scanning from -90 to 90 by every zero point 0.1 degrees. So this is in degrees. And then we also have the signal source properties and the number of signal to be one because we know that there's going to be one source of that beacon, of the signal, which is the beacon. So once we have that defined, the next step is we're going to simulate 500 pings from this beacon and then collect the data and use that to estimate the direction of arrival. Again, if you have the hardware, you're going to collect a bunch of data. It doesn't have to be 500 specifically. It could be any number. The more, the better. So I'm gonna do the same thing that you would do in a hardware, but I'm simulating how it would look if you collect a bunch of stuff. So let me run this section, and then this for loop is pretty similar to what we had before right here. Um, we simulated 10 pings from the, excuse me. We simulated 10 pings from the beacon. Here we're gonna just go for 500. All the steps are pretty much the same, except for this one, which is now using the music algorithm to estimate the direction of arrival for each ping. So we're getting 500 and then we're getting the estimate for each of them. Let me run this. It's going to take a second because there's 500 simulations. Once that is done, we can plot the angle. So this is the angle that the music algorithm has estimated. And we know the actual angle because this is a simulated system. And then you can see that, let me actually conduct this so I can zoom in and show you that the actual estimation is pretty close to the angle. So it's within a degree or two. Actually, it's within a degree. So this is 20 and 20.5. So um, within 1 degree of error. So that is pretty good for the system. Again, this is a pretty isolated system with very little noise. So this is, how an ideal system would work, pretty close to an ideal system. You might have to tune it a little bit more to get such good accuracy. And it also depends on how fast your sub or your boat is moving. So if you're moving pretty fast and changing directions frequently, that would also, be a source of lot of errors because again, it's hard to get the algorithm to converge when you're moving in different directions. So when you're doing the task for finding a finger, I would suggest moving in one direction, in a uniform direction. Sorry, in one direction, uniform speed, so that it's easier for your algorithm to converge. You can definitely work if you're moving in different directions. It's just going to take longer and might not have the highest accuracy. And once you have an algorithm, let's say you're using music and you're happy with what it's doing, you can also generate code out of it because right now everything is in MATLAB. But if you have your submarine or your boat that's running on a Jetson or a Raspberry Pi, you can generate C++ or C++ code from your algorithm and then just put it into your Jetson. So you don't have to run MATLAB or never run MATLAB in Jetson or Raspberry Pi. That's a terrible idea. What you should do is use it as prototype your algorithm, and then once you have that, you can always deploy performance C++ code that you can then run in your JITs and your Raspberry Pi or any other controller that you're using. If you are interested in code generation, I've talked about it a bunch in my previous webinars. If you go under RoboNation and look for MathWorks webinars, you'll see a lot of things on generating code out of the algorithms that you use. I'm not going to do the same thing again because I feel I've covered it enough. But if you are having issues with code generation, you can also reach out to me. I'm obviously available to help you guys out with this. And before I finish, I want to quickly go back to the documentation page and show you, um, like, sure. So this is something that you can use to test if your algorithm that you're choosing has code gen capabilities. So what you do is you choose one of the algorithms here, let's say beam scan estimator, and then you would go scroll down all the way to the end and then see that if it has C++ code generation. And this will usually give you some limitations. So that's usually along the data type size. So you'll have to be pretty you'll have to define your data types for this for code generation, obviously because it's C++. It needs to have all the size of your arrays and the data defined. So this is something that you can do, any algorithms or any function that you have in MATLAB. If you scroll down in the extended capabilities, you should see if that is supported in CodeGen, and if it is, what are the limitations that you might encounter. And that's it for the webinar. If there are any other questions, I can take that. So actually, the direction of arrival estimate itself is a pretty small part. But bulk of the webinar was actually simulating an acoustic beacon and a passive array. So this is useful if you're in a test pool and you don't have a beacon or you don't have a passive, or you don't have a hydrophone array. You can simulate different stuff and then also present this. So this is also useful if you, let's say you're running out of time for your competition, but you want to show the judges that you attempted this task. This would also gain you points in your when the judges judge you. I know this because I have judge teams. We look at the effort that you guys put in, and we see how much detail was included in your thought process. So if you include something like a detailed simulation that is shown here, that would count towards something in your report score and your design score. All right, Alicia, do we have any other questions?
You've had a lot of fans in the last few minutes of the webinar. And
Okay,
then one
that's
question,
fun.
one last question. They said, not as related to, not as much about this session, but how did you decide to start working at MathWorks?
Oh, that's an interesting question.
You've
I
gotten a
did
lot of
my
curveballs tonight. Yeah.
yeah, it's fine. When I was doing my master's, I was doing it in surgical robotics. That was something that I was really interested in. Um, and I actually did not use MATLAB a lot before that. So and then I used it for one of the courses that my professor taught, which was in MATLAB, and I found that it was pretty good. And then, of course, I was up when I was graduating, applied for jobs, and this was something that was in the robotics field, and this had a lot of marine robotics applications, something that I had not like worked in before. And I applied for it, and I got the job, and now I'm super happy because I get to learn a bunch of new stuff that I've never done before.
That is awesome. And we are very lucky to have you. Like you mentioned, you've been on the student side, but you've also been a judge,
Mhm.
so you understand what our students are going through. So you're very much the perfect
Yeah.
person to answer a lot of their questions. For those of you who are watching this later and aren't able to put it in the chat because it's no longer live, but you still have burning questions, we'll be sure to get Abhishek's email linked and everything so you're able to reach out. I know a few of you guys had some pretty tough questions today too, so if you still are burning for some answers, make sure you reach out to Abhishek and
Hmm.
learn more about that. And of course, for our RoboSub students, and I'm not going to try to steal your thunder if you were going to talk about it too, Abhishek, but we've got an
I
upcoming simulation award. So I'm going to pass it over to him because he's going to be the expert on what you need to do and how to get involved.
Yeah, as Alicia mentioned, we have a simulation award for RoboSub. This is worth $1,000 for the first place. And basically what we want to see is how you use MATLAB or Simulink for any task any task in your RoboSub competition. So it could be something as little as, how you use MATLAB for data analysis from different sensors, or it could be something like, designing 6-degree of freedom controllers for your sub, or uh, localizing your submarine in using the various filters that we have, or simulating the dynamics of your submarine, or anything that MATLAB with Simulink can do. If you have used our tools, uh, do apply for this award, because this doesn't require you to do anything extra. You just have to submit like a 5-minute video on how you used it. All the details are here. You just have to introduce yourself, what problems you face, and how you solved it, and then you can like participate in the award. You don't have to do anything extra. This is already included, and this is based on the task that you already have. So if you're using MATLAB or Simulink or any of our toolboxes, please consider applying for this award. It's a good way to get another $1,000.
Yeah. And it's also a great way to start practicing those soft skills before you head to
Mm-hmm.
the physical competition in Irvine later this summer. So we've emailed out some details about the simulation award, and we'll make sure we link those on Discord and send out some more emails in the future. But please, we really encourage all of you guys that are participating at RoboSub to submit this video. Like Abhishek said, you've already done all the work, so this is just your opportunity to brag about it and showcase how you've done it. To, as he mentioned earlier, to one of our judges, somebody that knows exactly what we're doing, but also our resident MathWorks expert. So this is a great way for you to showcase what you've done, but also learn and have a chance to kind of open up some of those conversations, maybe about in the future how you could use it more in different ways and things like that. And it's also awesome resume building material. So like you said, there's a little bit of money, there's a little bit of fun, and it won't take too much extra work for y'all. So please do it.
Yep. Thank you.
Thank you. If you don't have anything else, Abhishek, I just want to throw out another thank you again for helping us
Of
host this
course.
mini series with MathWorks. It's been a real treat to discuss over the last few months, just different sides of MATLAB and Simulink and all the things you guys are doing on your end. We know it's been incredibly helpful to our students. So please, if you haven't seen our first 2 webinars, make sure to check out our YouTube channel in the live section. We've got those 2 videos. We'll be sending out an email to our entire RoboNation community, just recapping this series and all of the sessions that we've had so far. And make sure you subscribe to our YouTube channel. We'll have more things like this throughout the year. But if this is the first time you've heard about RoboNation or the first time you've heard about MathWorks, make sure you either reach out to us. You can reach out to humans@robonation.org to learn more generically about RoboNation. And then you can reach out to Abhishek, whose email is right there, abshanka@mathworks.com, to learn more about MathWorks and all of the amazing stuff that they have available and do over there. So thank you for joining us, guys. And we look forward to seeing you during our next webinar on a topic that we have yet to announce, but we're excited to hear from you guys again. Have a good one.